This course consists mostly of tricks to try to solve various differential equations. This section is no different. Where I can, I will try to provide motivation for what made somebody even dream of the method, but sometimes it's just a matter of somebody playing around, taking derivatives and whatnot, and coming up with ways to solve these. So there's really not a lot of motivation, but we'll start with one that I see right like this. I got dy over dx plus y over x equals x. Now, using the method we had last time, you may try to separate it by doing the following. Dy over dx equals x minus y over x. Now, in order to separate, I would need the right-hand side of this equation to break up into factors involving only x and factors involving only y. But there's no way to do that here. I can't break this up. So this equation can't be separated. So that's where we have a trick. And the trick is to use something called an integrating factor. So let me put this here, the trick. What I'm going to do is go back to the original equation, dy over dx, but I'm going to rewrite the middle part to be 1 over x times y, and the right-hand side to equal x. Now, had that been a 0 to begin with, I would have been able to separate, but it's not. So I'm stuck in this situation here. Right here is the guy that I'm going to key in on, the 1 over x. This guy right there, I'm going to refer to it as phi of x, for reasons that will become apparent later. But for right now, what I'm going to do is I'm going to make a computation. The computation will look like this. E raised to the integral of 1 over x dx. When I integrate 1 over x, I get the natural log of the absolute value of x. But to solve this equation, I just need any old antiderivative will do. And one of them is just ln of x without the absolute value. It will make life simpler when I actually do this computation. Well, this simplifies to x. So this thing right here is referred to as an integrating factor. It's going to help us integrate when we need to. So the trick that we use is multiply everything by x. So multiply the differential equation by the integrating factor. So, taking my equation that was dy over dx plus 1 over x times y equals x, and multiplying the entire thing by x gives me the following equation. I'll have x times dy over dx. Of course, when I distribute the x through, it'll wipe out the 1 over x, and I'll get just plus y equals x squared. Now, the neat thing about this, here's what it does for us. Look at this side over here. Recall that if I take the derivative of x times y, that equals, well, on the one hand, I'll start with the derivative of y first, so I'll get x times the derivative of y. The derivative of y is nicely written as dy over dx. And then I'll have plus the derivative of x, which is 1. If you'll notice, this equals what I have on the left side of this equation. So I know that the left-hand side can be rewritten as d over dx of x times y. And the right-hand side is x squared. Then to finish this off, I'm going to multiply through by the dx. So I have d of xy, I'll explain this in a minute, equals x squared times dx. Now I'm ready to integrate both sides of the equation. All right, the left-hand side is actually very easy. You might, a little note maybe, is that if I integrate d of just anything really, say d of smiley face, then all I get back is the smiley face plus a constant. So whatever is the smiley face, that's what's left from the integration. So these cancel, the integral and the d actually cancel each other out. This is the differential of x times y. So I'll end up with just xy. I'll put the constant on the right as usual. That equals x cubed over 3 plus a constant. So this here is an implicit solution. That's fine unless otherwise asked. If you do have to get an explicit solution, I can divide everything by x, which automatically means that my answer is not good for x equal to 0, but anywhere else it's fine. So I'll divide by x, and I'll get y equals x squared over 3 plus cx to the negative 1, or c over x, whichever way you want to look at it. And so there's my final answer. So the trick can only be used, our integrating factor trick, to make this work, your equation must look something like this. You must have it in the format of dy over dx, plus I must have a function that is completely in terms of only x times a solitary y, and the other side can be any function of x as well. Then my integrating factor, I'll call it I dot f, will be e to the integral of phi of x. So there it is, right? This guy right here is the thing we're looking at. I'll do e to the integral of phi of x dx, and I'll multiply everything through by that. So I will get the equation e to the integral of phi of x dx times dy over dx plus e to the integral of phi of x dx times phi of x y equals e to the integral of phi of x dx times whatever function is on the right-hand side. Now, it's possible the right-hand side will not be an integral that you can do, but the left-hand side is, if you look at it, this piece right here now is the derivative of this piece. So here I have a function that I have not taken the derivative times the derivative of a function, y, plus the derivative of the first thing, leaving y alone. That's the product rule in action. I can compress that all to be d over dx of e to the integral of phi of x dx times y equals e to the integral of phi of x dx times g of x. I'm doing exactly what I did in the last step, or the last example. Multiply both sides by dx and then integrate. So I have d of e to the integral of phi of x dx times y will equal e to the integral of phi of x dx g of x times d of x. And then, of course, I'm going to integrate both sides. The left side is easy enough. The integral and the d will cancel out. Now I'll have e to the integral of phi of x dx times y. The right-hand side, who knows how complicated it can be. I don't even know that I'll be able to do it by hand, but it is all in terms of just x. So assuming you can integrate that side, you're fine. And then to get your final answer, you can divide by this quantity here to go and get y by itself if you should have to do that. So this is the trick. Each section will usually consist of about one trick that we will exploit as much as possible. So let me come back for just a second. I said, what is the motivation for this? Somebody made the notice that if they multiply by something like this, and e to something has the nice property that when you take the derivative of it, it stays there, but you have the derivative of the exponent appearing as a factor. That made it perfectly usable to make use of the product rule for derivatives. So, a little tricky. I don't know other motivation than if somebody was playing around someday and came up with a way of making the left-hand side compress. For our next example, basically what I'm going to do is just get these more complicated and messy examples as I move on. And part of your task is to be able to take a look at an equation and determine what techniques might work on it, just like anything else, really. This is not quite the way that I want it, because there is something in front of dy over dx. And I don't see it right now as being exactly the product rule in action just yet. While I have the derivative of y, 2 is not the derivative of x. So first thing I'm going to do is divide by x. And I'll get dy over dx plus, and I'm going to make it plain what I'm going to do. 2 over x times y equals 3 over x. So this way it is of the form that I want now. I have a function of x here in front of the y, and it equals a function of x. So this guy right here I'll use in my integrating factor. So my I dot f is going to be e to the integral of 2 over x dx. That'll equal e to the 2 ln of x, which right now I can't, that's pretty ugly as it is, but let me use a property of exponents with logarithms and take this 2 and move it as an exponent of x to get e to the ln of x squared. And the e and the ln will cancel, and that will give you x squared. So I'm going to multiply everything in the equation by x squared. And what that gives me then is I'll have x squared dy over dx plus, and the x squared times 2 over x will give me just 2x times y, and similar kind of thing happens on the right side. I'll end up with a 3x. So notice, look on the left. I have x squared, its derivative is 2x, and then I have the derivative of y, but leaving it alone is y. So this is a product rule. So the left side compresses down to d over dx of x squared times y equals 3x. And so you know what's going to happen next by now. Multiply through by the dx and integrate. Then the left side, the integral and the d will cancel out. It gives you x squared y. The right side will be 3 halves x squared plus c. And that is the solution unless I ask for an explicit solution, which means if I'm looking for an explicit solution, I will divide by x squared, and I will get y equals 3 half plus cx to the negative 2. Now, let me come back for a second here. This equation, if I had tried, going back to the original equation here, if I would have subtracted 2y from both sides, then I would have been able to separate the equation. So I didn't need to use this method for that. And separation would be the first thing that I would always try. Now, think about this. You don't need to get all of the solutions for this. That means I don't have to have a constant up here. You're just looking for something to try to solve the equation. So this is just so in particular, that one time when I did the natural log of without the absolute value of x, that just happened to be one particular antiderivative that made it so I could solve the equation. That's all that really matters here. So don't worry about having a plus here or anything like that in the exponent. Next one looks like x plus 2 squared dy over dx equals 5 minus 8y minus 4xy. Now what you want to do here is you want nothing but x on the right hand side. And it's okay to have something in front of it, but the first thing I'm going to do here is take anything with a y over to the left hand side. X plus 2 squared dy over dx plus 8y plus 4xy equals 5. It's not quite the way I want it just yet, so let me factor out a y from both of those pieces. So I have x plus 2 squared dy over dx plus, I can factor out a 4, I'll take out a 4y. So, I want to leave y by itself, so let me put y there. And that'll leave me with 8 plus 4x. And that is equal to 5. Now I'm going to divide both sides by x plus 2 squared to get it in the format that I want. So I have dy over dx plus 8 plus 4x over x plus 2 squared times y equals 5 over x plus 2 squared. Now notice here that I can factor a 4 out of this piece, and I can rewrite this as dy over dx plus, if I take the 4 out, I'll have 4 times 2 plus x divided by x plus 2 squared times y equals 5 over x plus 2 squared. And I'll be able to cancel out an x plus 2, so my next equation will look like this: dy over dx plus 4 over x plus 2 squared times y equals 5 over, and I just caught myself, that's just plain old x plus 2 down there. And 5 over x plus 2 squared. Now, it's not, remember, first thing I have to do is an integrating factor, so that keys in on this stuff. So my integrating factor, I dot f, is going to be given by e to the integral of 4 over x plus 2 dx, and that equals e to the natural log, well, 4 times the natural log of x plus 2. I'll play the same game I did before and take this 4 and make it an exponent. That equals e to the natural log of x plus 2 to the 4th power. And so now the e and the ln will cancel, and I'll get x plus 2 to the 4th. So had you been thinking about it, you perhaps could have come up with this, but look exactly with what I'm talking about. When I multiply through by this, I am going to have x plus 2 to the 4th times dy over dx plus. Now when I multiply x plus 2 to the fourth times this middle piece, I will get 4 times x plus 2 to the third times y. And on the right hand side, I'll get 5 times x plus 2 squared. And you can see it working. The derivative of this piece is 4 times this thing to the third power. See it? 4 times that to the third. So the left-hand side compresses very nicely. I get d over dx times x plus 2 to the fourth times y. And that equals 5 times x plus 2 squared. And so I'm ready to multiply by dx and integrate. So I'll have the integral of d of x plus 2 to the fourth times y. That equals 5 times the integral of x plus 2 squared dx. And then, of course, the integral and the d cancel. So you get x plus 2 to the fourth times y. And on the right hand side, I got 5 thirds times x plus 2 to the third plus c. Once again, leave your answer like that, or multiply through by divide through by x plus 2 to the fourth, and you can get y equals 5 thirds times x plus 2 to the negative 1 plus c times x plus 2 to the negative 4. Now for my next example, we haven't done one of these just yet, so I'll throw it in here. Suppose I give you theta times dr over d theta minus r equals 2 theta squared. Here, the independent variable is theta, the dependent variable is r, so r is like y and theta is like x. And we're also given this. Theta of 1 equals 5. So apparently the r values are a function of theta values as well. What this means is that when r equals 1, theta equals 5. We'll use that at some point to eliminate the constant. So right now it's not in the form that I want it to be in because I need to divide by theta to get the following. dr over d theta minus 1 over theta r equals 2 theta. So my integrating factor is e to the negative 1 over theta. And this, of course, be ln of theta, so this will be e to the negative ln theta. If I raise the theta to the negative 1, I'll get e to the ln theta to the negative 1, and of course that is just theta e to the negative 1, or 1 over theta. So I'll multiply everything by 1 over theta. And that gives me 1 over theta dr over d theta minus 1 over theta squared r equals 2. At this stage, you can be rest assured that the left-hand side is going to work just the way it has. The derivative of 1 over theta is indeed negative 1 over theta squared. So the left-hand side compresses to d over d theta of 1 over theta times r. The right-hand side, of course, is just 2. And then when I multiply through by d theta, integrate, I have the integral of d of 1 over theta times r equals the integral of 2 d theta. Well, the right-hand side is very simple. I get 2 theta plus a constant. The left-hand side is just 1 over theta times r. And so when I multiply through by theta, I'll get r equals 2 theta squared plus c theta. Now, I would be done normally, except I was given an initial value. Let's go back and find out what that was. The initial value is here. Phi of 1, or theta of 1 equals 5. So we have the initial value was theta of 1 equals 5, or r equals 1, theta equals 5. Let me plug those numbers in. So I'll put a 1 in for r, then I got 2 times 5 squared, that'll give me 50, plus 5c. That equals 1, so I'll subtract 50. I'll get negative 49 equals 5c. And so my c will equal negative 49 over 5. And thus, we get r, my final answer, r equals 2 theta squared minus 49 over 5 times theta. Incidentally, I haven't mentioned it before, but if you ever want to check your answers, take this thing and plug it back into the original equation and make sure you get what's on the right-hand side. For my last example, there's nothing special about what I'm doing here, except just showing you that a different format that this could occur, or the look of it looks different than the other ones, for instance. But rest assured, y prime is still dy over dx. I am going to give you an initial value of y of 0 equals negative 1. So when x is 0, y is negative 1. We'll deal with that when I get to the c part. Right here, there is the thing that I want to use for my integrating factor, I dot f. We would have e to the integral of tangent of x dx. This is one of those ones you're supposed to know. This equals e to the negative ln of cosine of x. Or you may have also learned that it's actually just e to the ln of secant of x. And you can see they're the same thing. If I took this negative 1 and put it as an exponent for cosine, you would get secant. The e and the ln cancel, and we just get secant of x. So I will multiply everything through by secant of x. So I'll get secant of x times y prime plus secant of x tangent of x y equals secant of x times cosine squared of x. And you can already see, since the derivative of secant of x is secant tan, the left side does exactly what it's supposed to and compresses down to the derivative of secant of x times y. The right-hand side simplifies a little bit because 1 secant of x destroys a cosine of x and will leave me with just cosine of x. Of course, the integral of cosine of x is sine of x. And on the left side, I get secant of x times y. And remember, this was an initial value problem, so the initial value that I had was y of 0 was negative 1. So I'll replace x with 0 and y with negative 1. So I'll get secant of 0 times 1, negative 1. That equals sine of 0 plus a constant. Secant of 0 is equal to 1. So I get negative 1 equals sine of 0, 0 of course, negative 1 is equal to c. So I get secant of xy equals a sine of x minus 1. Now if I want to get y by itself, I'll divide by secant of x. Well, if I divide by secant of x, that's no different than multiplying through by cosine of x. So I'll get cosine of x times sine of x minus cosine of x. And there is my explicit solution.